Prediction of monitoring indices. In general, most machinery defects are related to transmission systems, mainly for gears and bearings. In this work, gears are used as an example to illustrate how to apply the proposed integrated classifier for machinery condition monitoring. In operations, the fault diagnosis of a gear train is conducted gear by gear. Because the measured vibration is an overall signal contributed from various vibratory sources, the primary step is to differentiate the signal specific to each gear of interest by using a synchronous average filter, Wing et al., 2001. By this filtering process, the signals which are non-synchronous to the rotation of the gear of interest, for example, those from bearings, shafts and other gears, are filtered out. As a result, each gear signal is computed and represented in one full revolution, called the signal average, which will be used for advanced analysis by other signal processing techniques. Several techniques have been proposed in the literature for gear fault detection. However, because of the complexity in the machinery structures and operating conditions, each fault detection technique has its own advantages and limitations, and is efficient for some specific application only, Wing et al., 2001. Consequently, the selected features for fault diagnostics should be robust, that is, sensitive to component defects but insensitive to noise, i.e., the signal not carrying information of interest. In this case, three features from the information domains of energy, amplitude, and phase are employed for the diagnosis operation. 1. Wavelet energy function, using the overall residual signal which is obtained by bandstop filtering out the gear mesh frequency Fern and its harmonics, where Fr is the rotation frequency, in He, of the gear of interest and niche the number of teeth of the gear. 2. Phase demodulation, McFadden, 1986, using the signal average. 3. Beta kurtosis, using the overall residual signal. The details of these reference functions are listed in Appendix A. Based on the derived reference functions, the monitoring indices are determined to quantify the feature characteristics. Each index is a function of two variables, magnitude and position. The magnitude of an index is determined as the normalized relative maximum amplitude value of the corresponding reference function, the position is where the maximum amplitude is located. Usually, the maximum amplitude positions in these reference functions do not coincide exactly due to the phase lags in signal processing. Based on simulation and test observations, an influence window is defined as a period of 4 tooth periods in this case. Correspondingly, if all indices are located within one influence window, one set of inputs, x1, x2, x3, is given to the classifier. Otherwise, if three indices are not within one influence window, the object has no fault or has more than one defect, more than one set of inputs should be provided to the classifier. For example, if x3 does not fall within the influence window determined by x1 and x2, two sets of inputs will be given to the monitoring classifier. The first input vector is x1, x2, x3, where x3 is computed over the influence window determined by both x1 and x2. The second input vector is x1, x2, x3, where x1 and x2 are determined over the influence window around x3. Figure 3 illustrates an example of the reference functions corresponding to a healthy gear with 41 teeth. Figure 3a shows part of the original vibration signal measured from the experimental setup to be illustrated in Section 5. Figure 3b represents the signal average of the gear of interest, which is obtained by synchronous average filtering. Each wave represents a tooth period. Figs. 3c to 3e represent the resulting reference functions of the wavelet energy, beta kurtosis, and phase modulation, respectively. It is seen that no specific irregularities can be found from these reference functions for this healthy gear. Processing results for a healthy gear: A. Part of the original vibration signal. B. Signal average. C. Wavelet reference function. D. Beta kurtosis reference function. E. Phase modulation reference function. Figure 4 shows the processing results corresponding to a cracked gear with 41 teeth. It is impossible to recognize the gear damage from the original signal, Figure 4a. A little signature irregularity can be recognized around 200 in the signal average graph, Figure 4b. However, this gear damage can be identified clearly from the proposed reference functions, Figs. 4c to 4e. Although the maximum peak positions are little different from one graph to another, these peaks occur within one influence window, 4 tooth periods in this case. Processing results for a cracked gear: A. Part of the original vibration signal. B. Signal average. C. Wavelet reference function. D. Beta kurtosis reference function. E. Phase modulation reference function. Figure 5 illustrates the processing results for a chipped gear, with 41 teeth. Some signature irregularity can be recognized around 200 in the signal average graph, figure 5b, due to this gear tooth damage. However, this defect can be clearly identified from other three reference functions, figs 5c to 5e, and the monitoring indices are located within one influence window, 4 tooth periods. Processing results for a chipped gear: A. Part of the original vibration signal. B. Signal average. C. Wavelet reference function. D. Beta kurtosis reference function. E. Phase modulation reference function. System state forecasting is the process to predict the future states in a dynamic system based on available observations. Several techniques have been suggested in the literature for time series forecasting. The classical methods are the use of stochastic models, Gilad and Kusumano, 2004, which are usually difficult to derive for mechanical systems with complex structures. More recent research on time series forecasting has focused on the use of data-driven paradigms, such as neural networks and neural fuzzy schemes, C. and Atherton, 1999, Poromity, 2001. In this work, the multi-step ahead prediction of the input variables, indices, is performed by the use of a predictor as suggested in Wing and Verbenek, 2007, whose effectiveness has been verified. It can capture and track the system's dynamic characteristics quickly and accurately, and it outperforms to other related classical forecasting schemes. Given a monitoring index 1, ORCS 2, ORCS 3, if V0 V- or V-2 or V-3 R, represent its current and previous three states with an interval of R-steps, the R-step ahead stat of '+ R is estimated by a TS1 fuzzy formulation. Where BRMFs, SIG are constants, I equals 0, 1, 3, J equals 1, 2, 16, K equals 1, 2. Figure 6 illustrates its fuzzy reasoning architecture. The network architecture of the multi-step predictor. This NF predictor has a weighted feedback link to each node in layer 2 to deal with time explicitly as opposed to representing temporal information spatially. The context units copy the activations of output nodes from the previous time step, and allow the network to memorize clues from the past, which forms a context for current processing. This function of recurrent networks is valuable for predictors with limited n-step inputs, I.E.R1, to provide more information to the network so as to improve forecasting accuracy. If two sigmoid MFs are assigned to each input variable, the node output at the KTH process step will be where M equals 1, 2, I equals 0, 1, NV minus ER K and minus ER K minus 1, R, respectively, the input minus ER at the KTH and K1TH time steps, where K equals 1, 2, K, Ki is the total number of time steps, or training data sets. If a max product operator is applied in layer 3, and a centroid method is used for defuzzification in layer 5, by some related fuzzy operations, the predicted output '+ R can be determined by where mu macron J equals microjoule J equals 116 microjoules denotes the normalized roll firing strength, and mu J is the firing strength of the JTH roll. The fuzzy system parameters are trained by using a hybrid algorithm, that is, the premise parameters in the MFSB are trained by a real-time recurrent training algorithm whereas the consequent parameters SHIN, 8, are updated by least squares estimate, LSE. Details about the training algorithm can be found in Wing, 2008.